you are overpaying for backup power, and it's not even close. Right now, most Americans are told they need a $15 000 system to survive a blackout, when in reality, a $22 setup can keep your most critical devices running, if you understand how it works. That's not a small difference. That's the difference between being prepared and being completely dependent. The moment the grid goes down, because when it happens, and it will, your fridge shuts off, your internet disappears, and within hours, you realize how fragile your entire routine actually is. And here's the uncomfortable truth. It's not that solutions don't exist, it's that most people have never been shown a simple one. They can actually build themselves. In this video, I'm going to break down a low-cost power system built from basic materials you can find in the U.S., explain the exact science behind it, and show you what it can realistically power in a real-world outage. But before you assume this is the answer to everything, you need to hear this if you build it wrong. It won't work at all. And even if you build it right, there's a limitation that changes everything. It sounds impossible until the moment your power goes out and nothing else works. The moment the power goes out, everything you rely on stops instantly. Your refrigerator shuts down, and now every hour is a countdown to hundreds of dollars in spoiled food. Your internet drops. Your phone signal struggles, and suddenly even basic communication feels uncertain. The lights are gone, the HVAC is silent, and your home, something that felt stable just minutes ago, starts to feel fragile in a way most people never think about until it's too late. And if you've ever been through a multi-day blackout, you already know this isn't just inconvenient. It's disruptive on a level that hits your routine, your comfort, and your sense of control all at once. So what are your options? A gas generator sounds good until you deal with the noise, the fuel storage, the maintenance, and the fact that it only works as long as you keep feeding it. Battery backups, they're clean, but for most households, you're looking at thousands, sometimes tens of thousands of dollars, just to keep a few essentials running for a limited time. And that's the reality. Most solutions are either expensive, temporary, or both. And it's exactly in those powerless moments, when nothing works the way it should, that a different question starts to surface. What if the problem isn't electricity itself, but the way we've been taught to depend on it? Dan isn't a Silicon Valley engineer, and he's definitely not a YouTuber chasing clicks. He's a retired electrician from the Midwest who spent decades wiring homes, fixing outages, and dealing with the same problems you're dealing with right now. He understands power systems the practical way, not from theory, but from years of watching what fails when the grid gets pushed too hard. And the moment that stuck with him wasn't some technical breakthrough. It was walking into his own kitchen after a 3-day blackout and realizing everything in his freezer was gone. Hundreds of dollars lost, not because he didn't have access to electricity, but because he didn't have control over it. That frustration didn't turn him into an inventor overnight. But it did push him to ask a simple question most people never follow through on. Is there a cheap, simpler way to keep essential power running without depending on expensive systems? So instead of chasing new technology, Dan did something different. He went backward. He started looking at old ideas, basic principles, things most people dismiss as outdated or irrelevant, and began testing them in the most straightforward way possible. Right there in his own garage, he wasn't trying to create something revolutionary. He was trying to prove something practical. And in doing that, he stumbled onto something most of us never even think to consider. He wasn't inventing anything new. He was rediscovering something we collectively forgot. The first idea Dan tested was something almost everyone has seen at some point, the classic potato battery. You stick a couple of metals into a potato, connect a wire, and you get a tiny bit of electricity. It's simple. It's real. And it proves one thing. Clearly, energy can come from basic chemical reactions, not just expensive systems. But here's the problem. You already know a potato isn't going to power your fridge. And Dan knew that too. The concept worked, but the material was wrong. Unstable, inefficient, and nowhere near scalable for real use. Instead of throwing the idea out, he asked a better question. What if the principle is right? But the material is the limitation. That's when he shifted away from organic materials and started experimenting with metals, specifically ones that are cheap, widely available in the U.S., and capable of sustaining a reaction longer than anything biodegradable ever could. Aluminum stood out immediately. It's everywhere. It's reactive, and most importantly, it's something people throw away every single day without thinking twice. What started as a simple science experiment began to look like something more practical, something that could actually scale if handled the right way. And that's when Dan accidentally brushed up against a concept that had been around for decades, but almost nobody had ever tried to use it like this. What Dan landed on wasn't a brand new invention. It was something engineers have known about for decades. But almost nobody has ever applied this way, an aluminum air battery. And the reason it matters is because the science behind it is almost shockingly simple. You take aluminum, expose it to oxygen from the air, and combine it with a basic saltwater electrolyte. And that chemical reaction starts releasing electrons, usable electrical energy, no complex circuitry, no rare materials, no expensive manufacturing process, just a controlled reaction using things you can find almost anywhere in the United States. Now here's where it gets interesting, because this doesn't behave like the batteries you're used to. There's no plug to recharge it, no fast drain, followed by a sudden drop-off. Instead, it produces a slow, steady flow of power, almost like a drip system, rather than a surge. That means instead of delivering a burst of energy and dying quickly, it can keep feeding low-level electricity over an extended period of time, which is exactly what you need during a blackout reliability. Not spikes, and because aluminum is both cheap and widely available, the cost of building something like this drops dramatically compared to traditional backup systems. But here's the part that changes how you should think about it. This isn't powerful in the way most people expect. And that's exactly the point, because what makes it valuable isn't raw output, it's consistency over time. And that's the difference. This system doesn't win by being stronger, it wins by not stopping when everything else does. Dan's first prototype didn't look impressive, just a basic plastic storage bin. The kind you'd find in any American garage, lined with sheets of scrap aluminum, a couple of carbon rods pulled from old batteries, and a simple saltwater mixture acting as the electrolyte. No polished casing, no digital display, nothing that would make you think it could power anything meaningful. But the moment he connected a small load, a camp lantern, you could see it immediately. It worked. Not explosively, not dramatically, but in a quiet, steady way that most people would overlook if they didn't understand what they were looking at. From there, the process became systematic. He adjusted the spacing between the aluminum sheets to increase surface area, experimented with the concentration of salt, and added baking soda to stabilize the reaction, and tested different configurations to see how long the output could be sustained. One setup powered a light for hours, another kept a small fan running, and eventually, with enough refinement, he reached a point where the system could support essential devices, Wi-Fi, low-draw appliances, and even a compact refrigerator under controlled use. What mattered wasn't speed, it was durability. Each change wasn't about making it stronger, but about making it last longer, run cleaner, and operate more predictably. And with every iteration, the pattern became clear. This wasn't a fragile experiment, it was a system that could be tuned, adjusted, and scaled using simple materials and logic. At a certain point, the question stopped being, does this work? And became, how far can you push it? And that's when the setup in the corner of Dan's basement stopped looking like a project and started looking like a solution. At this point, it's easy to assume you're looking at a hidden breakthrough, but when an electrical engineer finally put Dan's setup through controlled testing, the results forced a different conclusion. On paper, the output wasn't impressive at all. The voltage per cell sat right where theory predicted, and the current was limited by surface area, meaning the system wasn't built to deliver high bursts of power or handle heavy loads the way a traditional generator would. In fact, if you measured it the same way you measure most batteries, you'd probably call it underpowered, but that's where the misunderstanding happens. Because when the engineer extended the test running it not for minutes, but for days, then weeks, the behavior became almost impossible to ignore. The output didn't crash, it didn't spike unpredictably, and it didn't degrade the way standard batteries do. It stayed consistent, delivering a low, steady stream of usable power far longer than expected, with minimal intervention, and suddenly, the metric that mattered wasn't peak performance, it was how long it could keep going when everything else stopped. That's the turning point most people miss. You're not looking at a system designed to win on strength. You're looking at one built to outlast. And it's exactly that weakness that allows it to survive longer than anything you've ever called a battery. To understand why this works, you don't need a PhD, you just need to see what's actually happening at the material level. Aluminum is a highly reactive metal, which means when it's exposed to oxygen and an electrolyte like salt water, it naturally begins to oxidize. That reaction breaks down the aluminum at the surface, and in the process, it releases electrons. Those electrons don't just disappear, they move through a connected circuit. And that movement is what we recognize as electric current. Now, in most systems, reactions are designed to happen fast, high output, quick energy release, and then a rapid drop-off once the material is consumed. But in Dan's setup, the reaction is intentionally restricted. Only a small portion of the aluminum is exposed at any given time, which slows the entire process down. And that changes everything. Instead of burning through material quickly, it creates a controlled, gradual release of energy, a kind of chemical drip feed that keeps producing electricity without collapsing under its own intensity. This is what people often misunderstand. It's not inefficient, it's deliberate. The system isn't trying to compete with high-power batteries. It's solving a different problem entirely. Put simply, it doesn't try to run fast, it just keeps running long enough to matter. The real shift didn't happen in a lab, it happened when the people around Dan started noticing something they couldn't ignore. During a local outage, while most homes on the block were completely dark, his basement system kept a few essentials alive. A neighbor walked over, saw a small fan still running, lights on, and more importantly, the Wi-Fi router still broadcasting a signal. That's the moment skepticism starts to break. Because it's no longer theory, it's something you can stand in front of and see working in real time. Soon after, Dan brought the setup to a small community hall and connected it to a basic load. A light, a fan, and a router. No noise, no fuel, no complicated installation, just a quiet system delivering consistent power. People watched as devices stayed on, not for seconds, but continuously, and the reaction wasn't excitement, it was confusion. Followed by curiosity, because if something this simple can work here, under normal conditions, it raises a bigger question about what's actually necessary. And that's when the idea starts to spread. Not because someone advertised it, but because people saw it function with their own eyes. When something works, not just in theory, but right next door, it stops being an idea and starts becoming a possibility. Once you understand the limitation isn't strength but output per unit, the next step becomes obvious. You don't rely on a single cell, you stack them. By connecting multiple aluminum air units in series and parallel, you can increase both voltage and current, turning a small, low-output system into something that can handle real-world demands. One unit might keep a router alive, but several working together can support lighting circuits, small appliances, and essential home devices during an outage. This is where the design shifts from a simple experiment to a modular system. You're not locked into a fixed capacity you build based on what you actually need. Add more surface area, increase the number of cells, and the system scales with you. It's not about replacing the grid. It's about covering the critical layer that keeps your home functional when everything else fails. At that point, the question isn't whether it works, it's how far you want to take it. Now, let's be clear about what this system is and what it isn't. It is not a full home replacement for the grid. You're not going to run central air conditioning, large electric heaters, or every appliance in your house the way you would on utility power. The current output is limited by surface area and reaction rate, which means high-draw devices will either drain it too quickly or simply won't operate efficiently. And if you expect it to behave like a gas generator or a high-end lithium system, you're going to be disappointed. But that's not the role it's designed to play. What it does exceptionally well is cover the essential layer, the devices that keep your home functional when everything else fails. Your refrigerator on a controlled cycle, your Wi-Fi router, lights, communication devices, the systems that determine whether a blackout is manageable or chaotic, and because it delivers steady, low-level power over time. It fills a gap that most expensive systems don't prioritize. Consistency without constant input. This is where expectations need to shift. You're not replacing everything, you're protecting what matters most. And once you see it that way, it becomes obvious this was never built to do everything. It was built to do exactly what you need when everything else stops. So if this idea has been around for decades and the materials are cheap and widely available, the obvious question is why you don't see it everywhere. And the answer isn't a hidden conspiracy, it's much simpler than that. It doesn't fit the current economic model. Large-scale battery systems, generators, and backup installations are built around high upfront costs, proprietary components, and long-term service cycles. That's how companies scale, how they generate revenue, and how entire industries sustain themselves. A system you can assemble from low-cost, accessible materials doesn't naturally fit into that structure. There's no subscription, no recurring upgrade cycle, no incentive for mass marketing. And there's another factor. Most people overlook this system requires understanding, not just purchasing. It's not plug and play. It doesn't come prepackaged. And it asks the user to engage with the process instead of outsourcing it. That alone limits adoption in a market built around convenience. So it's not that the idea is hidden, it's that it doesn't align with how products are typically distributed or promoted. It isn't ignored because it's impossible. It's overlooked because there's no clear reason for anyone to push it into the spotlight. What makes this concept move forward isn't advertising. It's people testing it for themselves and sharing what actually works. Once Dan's setup proved functional, others began building their own versions, adjusting materials, experimenting with configurations, and refining the design in ways no single manufacturer could replicate at scale. And this didn't stay local for long. Similar builds started appearing in rural areas, off-grid communities, and regions where access to stable electricity is inconsistent because the barrier to entry is low and the materials are widely available. You start to see the same pattern repeat. Someone builds a small system to keep a router alive. Another expands it to support refrigeration. And gradually, the design evolves through real-world use rather than controlled production. This is where the idea gains momentum, not as a product, but as a shared method. It adapts to different environments, different needs, and different resource levels without depending on centralized distribution. And that's what makes it resilient. Because once something can be built, understood, and improved by the people using it, it stops being limited to one place. Like most simple, effective ideas, it doesn't spread through promotion, it spreads through proof. Looking forward, the real potential of the system isn't in replacing existing infrastructure, it's in working alongside it. Imagine combining a slow, steady aluminum air setup with a small solar array. During the day, solar handles higher loads and recharges storage, and when sunlight drops, the aluminum air system continues delivering a consistent baseline of power without interruption. That kind of hybrid approach doesn't aim for maximum output, it aims for stability over time, which is exactly what most households need during extended outages or fluctuating grid conditions. And this is where the conversation starts to shift. Instead of thinking about energy as something you fully depend on or fully replace, you start thinking in layers: what needs continuous power, what can cycle on and off, and how to maintain control when the primary system fails. Systems like this open the door to a more flexible model of energy use, one that prioritizes resilience over scale. It may never dominate the market, and it doesn't need to. Its value comes from filling a gap that larger systems often overlook. It may not define the future of energy, but it's very likely to become part of how that future actually works. At the end of all this, the takeaway isn't that you've been missing out on some perfect solution, it's that you've been looking at the problem from a single angle. Most people think the answer to power instability is more capacity, more output, more expensive systems. But what this approach shows is something different. You don't always need more power, you need more control over the power you already depend on. And that shift changes how you prepare, how you invest, and how you respond when things don't go as planned. Because when the grid fails, the question isn't how much electricity exists, it's how much of it you can still access when you need it most. And for a lot of people, that difference determines whether a blackout is a minor inconvenience or a serious disruption. So now that you've seen how this works, I want you to think about it from your own perspective. Would you trust a system like this to support your essentials? Would you build it as a backup? Or do you think the limitations outweigh the benefits? Maybe you don't need a $15,000 system. Maybe you just need to understand what that $22 setup is actually doing. And the real question is, do you believe it works?